Next, we discuss the last and the trickiest type of projectile motion, which is a projectile along an inclined plane. So, here we have got an inclined plane, and let's call the starting point of the projectile, the projection point of projection, as the point O. It is from this point O that we project a projectile like this, making an initial velocity, having an initial velocity u, making an angle of beta, let us say, with this incline. Do you see there is already an inclined plane present here, an inclined plane which makes an angle alpha with the horizontal. And what we have done here is we have thrown or projected a projectile from the foot of this inclined plane such that its initial velocity vector u makes an angle beta with the plane of the incline itself, right? Now, as this projectile moves, it will go like a normal projectile only, but as it hits the inclined plane over here, that's where we consider the one complete motion of the projectile to have finished. So, as it reaches this point, let's call this point as B. As it reaches the point B, we say that the projectile has reached back to the inclined plane, and it is this motion that we are supposed to study now. Okay. So, there is a specific way in which we try to study this motion. We say that if this is the horizontal direction, the x-axis, right? This time what we do is we consider one more axis which is along the inclined plane, and we call it the x dash axis. Understand that the x dash axis makes an angle alpha with the x axis, right? And perpendicular to the x dash axis, we take our y dash axis, which is like this, y dash. And what we try to do now is we try to study the motion of our projectile along x dash and y dash as the two mutually perpendicular axes. Till now we have been studying it along x and y axis, right? Now we have kind of rotated our frame by an angle alpha, and we are now trying to study it along the x dash and the y dash axis. So, when we try to do that, see that we have to split our vector quantities along the x dash and the y dash directions. So, the first quantity that we can talk about maybe will be the acceleration due to gravity, which is acting on this projectile at all the times, right? As this projectile moves in air, the acceleration acting on it is still g, which is acting vertically downward. So, if you want to show that acceleration, it will look like this. It will act like this, vertically downward, g. This vertically downward direction this time, see that it will make, if we try to take up its components perpendicular to the incline like this, and along the incline like this by dropping perpendiculars from the tip of the vector g. We can understand from here that if this angle is alpha, the angle that the incline makes with the horizontal is alpha, then this angle will be 90 minus alpha. See that for yourself, because this g vector will be hitting this horizontal along a perpendicular. So, this angle has to be 90 minus alpha, and then this particular angle has to be alpha. So, if this angle is alpha, we understand that the component of g perpendicular to the incline along this direction will be g cos alpha, whereas the component of g along the incline along this direction will be g sin alpha, right? So, this time the acceleration that our projectile will have along the x dash and the y dash directions will be, see, acceleration along the x dash direction will be g sin alpha, and with a minus sign because it is pointing towards left, whereas we have taken the x dash direction along the right as positive, right? So, here we will say that ax dash is minus g sin alpha, whereas a y dash, acceleration along the y dash axis, will be this value, and again it is pointing downward, whereas we have taken x y dash along the positive, upward direction. So, can we say that this will also be minus g cos alpha? So, observe that this time we have an acceleration along the x dash axis also. So along both the perpendicular axis, the motion of the projectile is accelerated, but both the accelerations are still uniform. So we can still use the equations of motion. Also, both the motions will still be independent of each other because x dash and y dash as two axes are still mutually perpendicular, right? Also, we can find out the initial velocity along the x dash direction. Initial velocity along the x dash direction, as we drop a perpendicular from u along the x dash axis, will be nothing but u cos beta, whereas initial velocity along the y dash direction on the same lines, dropping a perpendicular from the tip of the vector u y dash here, will be u sin beta. All these basics we have already studied in the previous videos, right, about a normal projectile. So if there is any doubt, you can go back to those videos and just go through them to understand how these components are found. Now that we have obtained the initial velocities as well as the accelerations along the x dash and the y dash axis, we can try to find out our aspects associated with this projectile. For example, time of flight. The time for which the projectile is in air. See that for this particular figure, it is the time that the projectile takes to reach from the point O, the point of projection, to the point B, the point where it hits the inclined plane. Now to find out the time of flight, what condition can be put? What do we see happening at the point B where it hits the plane and completes its motion? Do we see that the point B lies along the x dash axis, which means that its y dash coordinate will be 0, right? So that means that the projectile, when it reaches the point B, its y dash displacement will become 0. See that as the projectile moves up from O, it will have some y dash displacement, isn't it? But then as it falls down and reaches back to the inclined plane, its y dash displacement will become completely 0. So this is one condition that we can use. So we put y dash is equal to 0 in, of course, the equation that connects the y dash displacement with the time, which is the second equation of motion, right? So y dash is equal to uy dash t, s is equal to ut plus half a t squared, right? We can now substitute our values over here. 0 is equal to u sin beta t minus half g cos alpha into t squared, right? And as we did it for a standard projectile, we can solve this. We can take t common to get u sin beta minus half g cos alpha t. This term should be 0. That means if the product of these two terms is 0, that means either this t should be 0 or this particular term should be 0. We understand that t is equal to 0 corresponds to the initial point of projection, right? So what we are looking for, the time of flight, we will get by putting this particular term equal to 0. When we do that, we will get u sin beta minus half g cos alpha into t is equal to 0, and that gives us the value of t, which has now become capital T, the time of flight, as 2u sin beta by g cos alpha. You can see for yourself doing the calculations. This is the expression for t that you will get. Now if you just recall the expression for t, the time of flight that we obtained for a standard projectile, see that in this particular expression all we need to do is replace g by g cos alpha to obtain the same relation t. If you remember, in a standard projectile the time of flight was 2u sin theta by g, where u sin theta there was the initial velocity component uy, right? So we are getting a similar relation here also, but see that the only difference is instead of g down here we have a g cos alpha. So that's all that we need to make a change, right, in the expression. Otherwise the expression is similar. So this is the time of flight. Now how to find out the range of this projectile? Range r. What is the range here? Coming back to the figure, the range is the distance between the point of projection O and the point B where the projectile hits the inclined plane. So the length OB is what we are looking for. Range is the length OB. Now how do we find out OB? Can we say OB is the displacement of the projectile along the x dash axis once it completes its motion? That means in the time which is equal to the time of flight, if we can find out the x directional displacement, that will be nothing but the range, right? So all we need to do is put t is equal to capital T, the time of flight, in the equation for displacement along the x dash axis, which is x dash is equal to ux dash t plus half ax dash t squared, right? This time ax dash is not 0, so we will have a second term also. Let's substitute this value. So we will have x dash will now become r is equal to ux dash we know is u cos beta into t. Now we need to put as time of flight. So it is this value of t that we substitute here as well as here. So we will have 2u sin beta by g cos alpha plus half into ax dash is minus g sin alpha, right, into 2u sin beta by g cos alpha whole squared. We have a t squared over here. So now we need to solve this expression. So in order to solve this, we can bring common terms together. So it will become 2u squared into sin beta cos beta by g cos alpha minus 2u squared into sin squared beta into sin alpha divided by g into cos squared alpha is what we will have here, right? Now we can take some terms common here. U squared by g cos squared alpha, let us take common, so that inside we are left with, see that 2 sin beta cos beta can be written as sin 2 beta. So sin 2 beta, and since we have taken a cos squared alpha over here, we will have a cos alpha coming up in the numerator minus 2 sin squared beta into sin alpha. Now using the trigonometric identity that 2 sin squared theta is 1 minus cos 2 theta, let's use that for this particular term over here, so that we get g into cos squared alpha here into sin 2 beta cos alpha minus twice of 1 minus cos 2 beta into sin alpha, right? Now when we open this up, see that we'll get a trigonometric identity. We'll have a sin 2 beta into cos alpha minus okay, this 2 is not there now, we have already used it in the formula, and when we open up the bracket, we'll get cos 2 beta into sin alpha. I've taken the product of these two terms first, and then there is a minus sin alpha which will remain separately. Now if you just look at it carefully, this is a plus, that this particular expression is nothing but the formula for sin of a plus b. So we can write it as sin of 2 beta plus alpha minus sin alpha, right? So this is the expression that we are getting, the simplified expression for the range of a projectile along an incline. Okay. From this formula, we can try to find out the maximum possible range. We can say that for R, the range to be maximum, what should be the condition for range to be maximum? Do we see that in this particular expression, this particular term is in sin, and if we look for the maximum value here, we can say that here sin should take its maximum possible value, which is 1, right? So we can say that for maximum R, sin of 2 beta plus alpha should be equal to 1, which is the maximum value of sin function, which then gives us a relation between alpha and beta, right? So for what value of sin is the value of sin theta 1? It's for the total angle being equal to pi by 2, 90 degrees. So can we say 2 beta plus alpha should be equal to pi by 2, 90 degrees? And from here we can say that this implies 2 beta is equal to pi by 2 minus alpha, or beta is equal to pi by 4 minus alpha by 2. So, this is one relation for which the range of the projectile along an incline will be maximum. If we just substitute this value back here into the expression and see what do we get for the maximum range as a result of this. Maximum range will then be u squared by g cos squared alpha into, now this first term has become 1, the maximum value, minus sin alpha, isn't it? Now, in order to solve this, what we can do is, we can write the cos squared alpha as 1 minus sin squared alpha. So, we will get a 1 minus sin alpha in the numerator and 1 minus sin squared alpha in the denominator, which will then cancel out to give us g into 1 plus sin alpha. Understand that here we have used the formula a squared minus b squared as a plus b into a minus b, right? So, this is what we are getting as the maximum range then, okay. Now, this method that we have used to find out the range has been a little tedious. It's mathematically, it's been a quite involved method. So, what we do is we try to find out another method, a substitute method to find out the range of the projectile. Another method to find R. See carefully, this is an interesting method. What we do now is, considering the same projectile along an inclined plane with the incline making an angle alpha with the horizontal, right? If we project our projectile like this so that it hits the inclined plane somewhere here at the point B, understand that if we know the value of alpha, beta and u, we can still consider the motion of the projectile along the x-axis, along the horizontal axis. Along the horizontal then, we know that acceleration of the projectile is 0. So, it moves with a constant velocity. This remains constant, not ux, vx remains constant. The velocity along the x-axis remains constant, and hence the displacement along the x-axis is simply vx times t, which in this case will be ux also times t, which is u cos alpha plus beta times t, right? Alpha plus beta becomes this total angle and it gives us the component of the initial velocity along the x-axis. Now, using this, if we try to drop a perpendicular from the point B down to the x-axis and say that, let's say this point where it hits the x-axis is the point P. Do we understand that if we can find out this length OP from the point of projection to the point P, this length OP will be nothing but the displacement along the x-axis in a time capital T. Understand that the projectile hit the inclined plane point B at a time capital T, isn't it? And at that time, its x directional displacement was the length OP, right? So, can we say the length OP, which is the x directional displacement for the projectile's whole path, will be the velocity along the x-axis times capital T, the time of flight, right? What will that be? Can we say it will be u cos alpha plus beta, which is the velocity along the x-axis, times capital T we have already obtained. In the previous exercise, we saw that the time of flight of a projectile along an incline comes out to be 2u sin beta by g cos alpha, right? So, this expression we have got now as the horizontal displacement, this value, this length, particular length OP of the projectile as it hits the incline. Now, let us look at the triangle OPB. In triangle OPB, do we see that OP by OB is nothing but cos alpha? So that we can write OB, which we are looking for, is equal to OP by cos alpha. And now all we need to do is substitute this particular value of OP over here in this expression to get the range. So, that implies range R, which is nothing but the length OB, will be OP, which is u cos alpha plus beta into 2u sin beta by g cos alpha divided by cos alpha, which will make this cos squared alpha. So see that here we have been able to get this range in quite an easy method. It's very simple method used in comparison to the previous one, right? So you can directly use this to find out the range. Generally we employ this method directly into questions. We don't really try to find out this formula and by heart it. We don't by heart these formulae. We use the basics. We understand what basics we have employed here and we use those basics directly into the questions. Okay. So in the next class, we shall look up at a few examples related with a projectile along an inclined plane.